In our previous lessons, we have learned about the various principles which are used in counting. To name the few, we have learned multiplication principle, addition principle, bijection principle, contradiction principle. We will learn few more principles. So the first one we will be learning here is the pigeonhole principle. It is one of the most easiest and quite intuitive of the principles among the countings. So it simply says if you have more pigeons than holes, that needs to be placed. The pigeons needs to be placed in the holes, and if you have more pigeons than holes, then at least one of the holes will have more than one pigeon, right? So let's see how we are going to. Let's try to visualize it. So let's say we have 6 pigeons and 5 holes, right? So you can always place the 5 pigeons in 5 holes, like the way which we have put now, right? But again, you see we have the 5 holes as like this. So these are your 5 holes, and we have placed one pigeon here. Now we are still left with one pigeon which needs to be placed in any one of the holes, right? So you can place that pigeon in either here or anywhere. Still, in all these 3 cases, we'll have one hole which have more than one pigeon, so that is 2 pigeons, right? So this is the basic of pigeonhole principle, but we would like to write that formally into mathematics in mathematical terms, and we denote this principle as PP as a short form, as an abbreviation. So how do we write that mathematically? So let n and k be the 2 numbers that belongs to number m, and n is greater than k. Then if we have to place n objects in k containers, right, then at least one of the container will have more than one object. So this is the basic principle of pigeonhole, and we will now moving to the next generalization principle on pigeonholes, which we say, and we'll also try to prove it. So it says that if we have m pigeons to be placed in k holes, then at least one hole will have more than, this is floor, right? Floor of m minus 1 divided by k. So we will define what this floor of any number means. Floor is nothing but it is the minimum integer value, right? So 10 by 3 is 3.3, so its integer value is 3. Similarly, if you try to find the floor of 5 by 8, it will be 1 point something. So the minimum integer value will be 1, right? Now we'll move to the proof of this, that if we have m pigeons to be placed in k holes, then at least one of the hole will have more than m minus 1 k pigeons. So we take 2 cases here. The first case is k is greater than m, so there are more holes than pigeons, right? So more holes than pigeons, then we have m minus 1 by k, floor is 0 because this number lies between 0 and 1. So the minimum integer value will be 0. Now it is obvious that at least one of the holes will have more than one pigeon, 0 pigeon, because we have to place at least one pigeon somewhere, right, in any of the holes. Now let's take the second case, and we define a number n such that nk plus 1 is less than m, and n plus 1 into k is greater than m. Now we divide. Now let's try to divide the n. Now we will place n minus 1 pigeons in each of the holes, right, in the k holes, in each of the k holes. So we have already distributed k into n minus 1 pigeons, right? We also note that m minus 1 by k floor in this case will be n, right? So we have to look it carefully here. We will just write it down. I'll just write it down. So if m is less than nk minus 1, so the minimum value of m could be nk plus 1 minus 1 by k, right? So we have to find the floor of it. 1 gets cancelled. So this is again n, because k and k gets cancelled. Now this value is also in between n plus 1 into k. So we'll put that value now as m. So we'll have this thing. Yep. This is 1, and this is nk plus n. Sorry, k, right? K, and we also have minus n plus 1 into k. Yeah, so this is 1 by k. Now if you pay a close attention, this will be nothing but n plus 1 minus 1 by k by k. So this integer we will list with 1 by k, and since k is a positive number, so this the whole value of this will be again n. In both the cases, the floor of these two numbers are n, right? Now, so what we'll do is that we will divide first all n minus 1 pigeons in all the holes, right? So how many pigeons we are left with now? So minimum value of pigeons we have is nk plus 1. So the nk minus 1 minus n minus 1 into k is nothing but 1 plus k. So at least there will be 2 pigeons left to be placed in one hole, right? Because k is a positive integer greater than 1. So we have at least 2 more pigeons to be put, and henceforth, and we have already put n minus 1 pigeons. So at least 2 more pigeons will go into at least one hole. So we will have n plus 1 pigeons in a particular hole, which says that it should be more than this. So we have already got that at least in one of the holes we will have to put n plus 1 pigeons, right? Now let's take a few of the examples of pigeonhole principle so that we understand it better. So we have a question like so that among any 4 integers there are 2 integers whose difference is divisible by 3. So it could be any 4 integers like 1, 9, 57, 28, whatever, any 4 integers you can choose, and then it says that the difference of all the there will be at least 2 integers whose difference will be divisible by 3. Now how we are going to prove that? So we have 4 objects here, right? And we will define 3 boxes where we can place these 4 objects. So these 3 boxes will be the box 1 where if the number is put, it should be divisible by 3. That such that this kind of a number can be represented as 3x. The box 2 will be where the remainder is 1, so this can be represented as 3x plus 1, and box 3 will be where the remainder is 2. So if you divide any number by 3, you will get either remainder 0, 1 or 2. So we can only put all these 4 numbers into these 3 boxes only, right? So we have this box 1, box 2, box 3. Again, by the pigeonhole principle, at least one of the box should have 2 such numbers, right? So let's say that the B2 is such box, right, which has such 2 numbers. So it will be in the format 3x plus 1 and 3y plus 1. Similarly, if there are B3 is the box where 2 of the integers will fall, then it will have 3x plus 2 and 3y plus 2. Similarly, B1 is the box where 2 integers will fall, then it will be 3x and 3y. If you take a difference, then it will be always 3x minus y, meaning y it is divisible by 3, right? So this is one of the basic example of proving something using the pigeonhole principle. Now we will take a slightly more complex problem. So it says that in any group of 6 people, there are 3 people that mutually know each other, or 3 people that mutually do not know each other, right? So when we say mutually, so let's say there are 3 people A, B, C, then A, and when we say mutually know each other, means A and B should know each other, A and C should know each other, and B and C should know each other, right? So this is the meaning of the mutually know each other. Now we take any person and we call that person as A, right? Now we can again, define 2 boxes, or let's say 2 holes, where such that it should be disjoint and it should form the complete set. So let's say these boxes are defined as if the person is placed into this box, it means he does know A, and if the person is placed in this box, that means he does not know A. So these are the 2 different boxes or the holes, and there are 5 people left which need to be placed here, right? So there are 5 pigeons and 2 holes. So by the pigeonhole GPP, generalized pigeonhole principle, we know that this number, at least one of the box, either this one, this is let's say hole 1, or this is hole 2, right? So either H1 or H2 must contain 3 objects, right? Because 5 minus 1 by 2 is 2, so it should be more than 2. So at least one of them will have 3 objects, right? Now let's name these three person or objects as A1, A2, A3. Now there could be two possibilities that either A1, A2, A3 mutually don't know each other, or they don't know each other at all. Or the second possibility here comes that either A1 or A2, one of the pair A1, A2 or A1, A3 or A2, A3 know each other, right? Now I'll prove this in the case that A1, A2, A3 falls in H1, right? So if they don't know each other mutually in the first case which we have discussed here, then we get the three people such that they don't know each other. So they will lie in this group. Now let's say suppose A1 and A2 know each other, but A1 knows A as well and A2 also knows as well. So there will be three mutually people who know each other, and these three people will be nothing but A1 and A2. So we are able to prove that there are at least three people who actually mutually know each other, or there are three people who mutually don't know each other. Please note the pigeonhole principle is normally used to prove something. It is not used to count something. But this is one of the very important principle which we will use very often while proving the various things in the counting, right? The next principle which we will be discussing is the principle of Pauli inclusion exclusion principle in the next session, right? So that's it for now. Thank you.